In this video, I will give you more examples on the differentiation of trigonometric functions. Okay, so in the following examples, we just find the first derivative of the function. In number 8, we'll have the function y equals ln of cotangent of x squared. Okay, so this function is actually a logarithmic function where u is equal to cotangent of x squared. So if we recall the differentiation formula for ln of u, the derivative of ln of u is equal to 1 over u times du. So in this case, in our example, u is equal to cotangent of x squared. So u is a trigonometric function. So in the derivative of y with respect to x, using the formula for the derivative of ln of u, dy over dx is equal to 1 over u, where u is cotangent of x squared, times du. And du is the derivative of cotangent of x squared. Okay, so we're not done yet with the differentiation process. We still have to get the derivative of cotangent of x squared. We recall the formula for that. The derivative of cotangent of u is negative cosecant squared of u times du, where u is the angle. In this case, it's x squared. This is u. Alright, so in dy over dx, we have 1 over cotangent of x squared times the derivative of cotangent of x squared using the formula. It's negative of cosecant squared of u, where u is x squared, times du. So that's the derivative of x squared. Now using the power rule to get the derivative of x squared, we'll have 1 over cotangent of x squared times negative cosecant squared of x squared. The derivative of x squared with respect to x is 2x. So we are done with the differentiation process. We'll just have to simplify our final answer. Okay, so in simplifying our final answer using a reciprocal identity, we know that the reciprocal of cotangent function is tangent function. So this can be written as tangent of x squared using an identity. And then let me just write 2x in this here, and then followed by negative cosecant squared of x squared again. Okay, now simplifying further, let me just write negative 1, this part, here beside 2x, so it's now negative 2x, our constant is negative 2. And then let's write tangent x squared using sine and cosine function. So that is by using a quotient identities. Tangent function is equal to sine over cosine, so that's sine of x squared over cosine of x squared using a quotient identity. And also writing cosecant squared of x squared using sine function. So that is by using a reciprocal identity. You know that the reciprocal of cosecant function is the sine function. So that's times 1 over, that's cosecant squared, so that is 1 over sine squared of x squared. Now let's simplify further. We can divide sine of x squared and sine of x squared, so this will be cancelled out in the numerator, while the exponent of sine of x squared in the denominator will become 1. And so we're rewriting our answer. Dy over dx is equal to negative 2x in the numerator, and in the denominator we have cosine of x squared times sine of x squared. Okay, so recalling again the double angle identity of sine function, sine of 2 theta is equal to 2 sine theta cosine theta. Well, in this case, in our example, theta is equal to x squared. Okay, so we see this portion, sine theta cosine theta, here, where theta is equal to x squared. Okay, so if we divide both sides of the identity by 2, then we'll have 1/2 of sine 2 theta equals sine theta times cosine theta. And that's exactly this part. So cosine x squared times sine x squared is equal to 1/2 sine of 2 times x squared. Okay, so that's 1/2 sine of 2 times x squared. I'll just write theta as x squared equals sine of x squared times cosine of x squared. So the denominator can be written as 1/2 sine of 2 times x squared. Right? So rewriting. Okay, that's it. After using the double angle identity. So multiplying 2 and 2 in the numerator, we'll have negative 4x over sine of 2x squared. And of course, we know that we have used this identity a while ago. The reciprocal of sine function is cosine function. We know that 1 over sine cosecant function. Theta is equal to cosecant theta. So our final answer is dy over dx equals negative 4x. The reciprocal of sine function is cosecant. Okay, theta here is 2x squared. This is the derivative of the function in simplified form. Next example, we have the function, let's use f of x equals cosine of ln of 2x. Okay, so this time, this is a trigonometric function where u is equal to ln of 2x. This is u. Let's recall the formula for cosine, the differentiation of cosine of u. Derivative of cosine of u is equal to negative sine of u times du, where u is the angle of the trigonometric function cosine. Alright, so f prime of x using that formula is equal to negative sine of u, where u is ln of 2x, times the derivative of u, where u is ln of 2x. Now we recall again the formula for the derivative of ln of u. Derivative of ln of u is 1 over u times du. So in this case, this is u. So f prime of x is equal to negative of sine of ln of 2x. The derivative of ln of 2x is 1 over 2x times the derivative of u, where u is 2x. Let's continue in the differentiation process. We'll have negative sine of ln of 2x times 2x, 1 over 2x. The derivative of 2x with respect to x is 2. Okay, so simplifying, we'll have 2 over 2 equals 1. And so our final answer, the derivative of f of x is equal to negative sine of ln of 2x. In the denominator, we'll just have x. This is the derivative of the function. Another example, we'll have the trigonometric function secant squared of e to the negative 4x. The angle here is e to the negative 4x. Okay, so let's be clear that this function is a power of secant of u. Okay, so we're going to use the power rule here, the general power rule, of course. We can rewrite the function as g of x equals the secant of e to the negative 4x. This is raised to 2. Okay, so this can be differentiated using the general power rule, where u is equal to the base. Of course, in the general power rule, the base is always equal to u. So let's just recall the general power rule. General power rule, the derivative of u to the n is equal to n times u raised to n minus 1 times du. This is the formula that we're going to use. Okay, so the derivative of g of x using the general power rule is n times u, where u is the base, secant of e to the negative 4x. Okay, now n minus 1 will give us 1 as the exponent of secant function. So this will just be raised to 1. No need to write that anymore. Times du, where u is secant of e to the negative 4x. We're not done with the differentiation process yet. So in the derivative of secant of e to the negative 4x, we'll have to use the formula for the derivative of secant of u, where it will give us secant of u tangent of u times du. So in this case, in our differentiation, this is u. Okay, so rewriting g prime is equal to 2 times secant of e to the negative 4x. Okay, so the derivative of secant of e to the 4x using the formula for the derivative of secant of u is secant of u, where u is e to the negative 4x, times tangent of u, where u is e to the negative 4x, times du, where u is e to the negative 4x. Okay, so to differentiate e to the negative 4x, we recall the formula for differentiating e to the u. It's e to the u times du. In this case, u is equal to e to the 4x. Okay, let's continue with g prime of x. It's 2 secant of e to the negative 4x. Let me just copy everything. E to the negative 4x tangent e to the negative 4x. The derivative of e to the negative 4x using the formula for the differentiation of e to the u. So it's e to the u, e to the negative 4x times du, where u is the derivative, where u is negative 4x. So it's a derivative of negative 4x. Okay, now we can multiply this too. So we can just write it as, so it's 2 times secant squared of e to the negative 4x. Okay, secant of e to the negative 4x times itself is secant squared of e to the negative 4x. So that's it. So tangent, okay, tangent of e to the negative 4x. I missed the negative 4x here. Negative 4x, okay, times e to the negative 4x. The derivative of negative 4x with respect to x is equal to negative 4. Okay, so let me just write this 2 in front. So g prime of x, if we multiply negative 4, this constant, and 2, we'll have a negative 8 as a constant. And then I'll write this in front also, e to the negative 4x. And then the remaining expression, secant squared of e to the negative 4x times tangent of e to the negative 4x. This is the derivative of the function. In the next example, you're given y equals the product of e to the x and sine x. We find the second derivative of y with respect to x. Okay, this is a product of two functions, where the two functions are e to the x and sine of x. So let u be equal to the first factor, and let v be equal to the second factor sine x. Okay, so in that case, we'll have du equals the derivative of e to the x, so it's just e to the x itself, times du. U here is x, so du would just be equal to 1. Okay, and dv, according to the formula, is equal to cosine of x. So y prime, using product rule, just to recall the product rule, derivative of u times v is equal to u times dv plus v times du. So y prime is equal to u e to the x times dv cosine x plus v sine x times du, where du is equal to e to the x. So it's just e to the x cosine x plus e to the x sine x. This is the first derivative of the function. So you have two options here. You may factor out the e to the x, the common factor e to the x, or you may leave it as is before we differentiate again y prime. So if we differentiate y prime again, we'll have y double prime. So if we factor out e to the x from the two terms, we'll have e to the x times cosine of x plus sine of x. Okay. Differentiating this again, we'll have y double prime, and it will be the derivative of u times v, where u is equal to e to the x and v is equal to this. Okay. So in that case, du is equal to e to the x again, while dv is the derivative of cosine of x plus sine of x. So the derivative of cosine of x is negative sine of x, plus the derivative of sine of x, which is cosine of x. Okay, so y double prime, in this case, y double prime is equal to the derivative of e to the x times cosine of x plus sine of x using the product rule. So the same product rule above, it's e to the x, so u times dv, where dv is negative sine of x plus cosine of x, plus v times du, cosine of x plus sine of x, times du e to the x. Okay. So to combine like terms, you have to remove all the grouping symbols. So distribute e to the x inside the parentheses. We'll have negative e to the x sine x plus e to the x cosine x. Okay, plus e to the x cosine x plus e to the x sine x. So combining these two, we'll get a 0. And then combining the other two terms, we'll have 2 e to the x cosine of x. This is the second derivative of y with respect to x. In number 12, we have the cosine of the function y equals cosine of 3x. So we need to find the 45th derivative of the function. Okay? So we don't have to go through the first until the 44th derivative to find the 45th derivative of the function. What we need to find here is a pattern. Okay? So if you see the pattern already, you can stop the differentiation and analyze what's the 45th derivative of the function. So we start with the first derivative of the function. We recall the formula for the derivative of cosine of u. I hope you remember this by now. It's negative sine of u times du. So the first derivative of the function is negative sine of u, where u is 3x, times the derivative of 3x. What's the derivative of 3x with respect to x? It's 3. So I'll write the constant here in front. So that is y prime. What is y double prime? Y double prime is the derivative of negative 3 sine of 3x. So recalling the formula for the derivative of sine of u, it's cosine of u times du. So we'll just copy the constant, negative 3, take the derivative of sine of 3x using the formula on the right. So it's cosine of u here is 3x times du. Again, the derivative of 3x is 3 with respect to x. So we can write this as negative 3 squared. So 3 times 3 is 9, or it can be written as 3 squared cosine of 3x. We're trying to look for a pattern here. Now, the third derivative of the function is the derivative of negative 3 squared times cosine of 3x. Well, we'll just copy the constant, negative 3 squared. The derivative of cosine of 3x is again sine of 3x times the derivative of 3x. That's 3. We can write this as negative 3. Nope, we missed the negative sign. The derivative of cosine of 3x is negative sine of 3x times 3. Okay, so if we simplify this, we have here a negative 1 times another negative 1. We'll have a positive 3. This time we have 3 squared times 3, so it's 3 cubed sine of 3x. Now we are on to the fourth derivative. We change the notation. Okay, the fourth derivative of y with respect to x is the derivative of 3 cubed sine of 3x. That's just a constant 3 cubed, so we just copy. The derivative of sine of 3x is cosine of 3x times the derivative of 3x, which is 3. Simplifying, we'll have 3 to the fourth. 3 cubed times 3 is 3 to the fourth cosine of 3x. Now what is the fifth derivative of the function? The fifth derivative of the function is the derivative of 3 to the fourth times cosine of 3x. So the constant 3 to the fourth will just be copied. The derivative of cosine of 3x is negative sine of 3x times 3. So the result now is 3 to the fifth times negative sine. So I'll write negative 1 here. Negative 3 to the fifth times sine of 3x. Now let's look for a pattern here. You see here, the given is cosine of 3x. And then the first derivative is negative sine of 3x. Third derivative is again a negative expression, negative 3 squared cosine. And then the second derivative is negative 3 squared of cosine of 3x. And the third derivative is 3 cubed sine of 3x. Again, it's positive sine. So the function is positive cosine. The first derivative is negative sine of u. The second derivative is negative cosine of u. The third derivative is positive sine. If we go to the fourth derivative, we're back to positive cosine of u here, with a multiplier 3 to the fourth. Okay. In the fifth derivative, we're back to negative sine of 3x with a multiplier of 3 to the fifth. If you try to look for a pattern in the constant, look at the exponent of 3. In the second derivative, we have here 2, the exponent of 3. In the third derivative, we have the exponent of 3 is 3. In the fourth derivative, we have the exponent of 3 is 4. In the fifth derivative, we'll have the exponent of 3 as 5. Okay, now, the derivative is actually a cycle of 4. Look at the pattern. So, every fourth derivative, we go back to the same given. We go back to cosine of 3x. Look at the fourth derivative. We're back to cosine of 3x. So, in the eighth derivative, the function will again be cosine of 3x times a multiplier, which is a power of 3. Now, the exponent of 3 is based on the number of derivative. Okay, so if this is the eighth derivative of the function, the exponent of 3 would be 8 also. So, in the next multiple of 4, that's 12. The 12th derivative will actually be equal to 3 raised to 12 times cosine of 3x again. Now, what is the last multiple of 4 before the 45th derivative? So that would be the 44th derivative. That is 44. The last multiple of 4 before 45 is 44. So the 44th derivative of the function will be 3 raised to 44 based on the pattern times cosine of 3x again. Okay. Now what is the derivative of cosine of 3x? That would be negative sine of 3x times 3 again. Okay, so we'll be able to get the 45th derivative of the function is the derivative of 3 to the 44th, which is just 3 to the 44th times the derivative of cosine of 3x. So that's sine of 3x, or negative sine of 3x, times 3. So the 45th derivative of the function is negative of 3 to the 45, okay, 3 to the 45th power times sine of 3x. It's according to the pattern. So we don't have to go through the first till the 45th derivative to find our final answer. Okay, because looking at the first 5 derivatives of the function, we have already seen a pattern here. So that every after 4 differentiation processes, we'll always have this. Okay, and so the last multiple of 4, because we have the cycle of 4 here in the pattern. The last multiple of 4 before 45 is 44. So the 44th derivative will again be equal to the given function cosine of 3x times a multiplier. In this case, the multiplier in the 44th derivative is 3 raised to 44. So upon differentiating that, we get the 45th derivative of the function. Okay, that's it.